So I wanted to give a quick intro to acids and bases. We've talked about acids before, we've named them, and a couple of examples here on the screen in sulfuric acid, H2SO4, and hydrochloric acid, HCl. A couple of other properties about an acid. An acid will turn litmus paper pink, as you can see in the bottom left-hand corner of the screen. Acids will react with a lot of metals, and we might even say they dissolve metals. And they often will taste very sour. And so if you've had licked a lemon or eaten a lemon or had a good orange, you know that sour flavor is there. And that's citric acid that's in citrus fruit. So there are a couple of definitions of acids. We're going to look at two. One is called the Arrhenius definition of an acid. And in this definition, the acid is something that when it is dissolved in water produces hydrogen ions. And that's the definition we worked on, or that we used when we named acids. So it had to have hydrogen in it. And so you see the example down here of HCl, and it has a hydrogen ion in it. And when it's dissolved in water, right, that's the AQ, it's going to produce hydrogen ions, and it's going to produce chloride ions. According to the Arrhenius definition, that hydrogen ion production specifies that HCl is an acid. So more specifically, that hydrogen ion, we would call it a hydronium ion, because it doesn't just exist as H+, it will connect with water, because hydrogen is a positive charge, and the oxygen in water has these two lone pairs of electrons, right here and right there, and they will be very attractive to the positively charged hydrogen ion. And so the water and the hydrogen ion will connect, and we'll get this thing called a hydronium ion. That's just kind of the formal way of saying it. When Arrhenius came up with his definition, probably didn't quite understand that that's what occurred. And oftentimes we will just use H+. But please realize that they will always, as it says here, associate with H2O. We'll use them interchangeably. H+ is certainly quick and easy, but hydronium is formally the right way of expressing it. So just a brief review here of some of the acids and how to identify them. When you've got a molecule, and most acids are molecules, when they are written, the hydrogen that is the one that kind of pops off and produces the hydrogen ion in solution is often written first. And so this can look like the combination of a hydrogen and what's known as a formate ion. That's just another polyatomic ion. It's one you guys didn't have to memorize, but that's the one that's in this example. So if this were not dissolved in water, we'd call it hydrogen formate. But when it is dissolved in water, we would call it formic acid. And if we were to look at the structure of it down here, we would see that there would be this one hydrogen, and this is the ionizable hydrogen, the one that when it's dissolved in water, we get a hydrogen ion. And so if we were to dissolve this one in water, the formula would look, or the equation would look something like this. HCHO2 aqueous, that means it's dissolved in water, becomes H+ and CHO2-. Now don't tell my AP Chem students that I did it that way, because they'll be up in arms, because I would never let them do it that way. Of course, you want to put the aqueous in here, but there are a few more details with some acids that you have to follow. But we're just going to look at this just to get an idea of the definition and to what goes on when it is dissolved in water. So then there's the definition of a base. And a base is something that produces hydroxide ions when it's dissolved in water. And so you can see the equation down here on the right. Sodium hydroxide, when it dissolves in water, produces or dissociates into sodium ions and hydroxide ions, right? The two ions that make up sodium hydroxide, right? The sodium ion and the polyatomic ion hydroxide. Remember way back to when we did polyatomic ions. And so when you're looking at chemical formulas and you see an OH in the chemical formula, that might be an indicator that that substance is going to be a base. One other aspect of Arrhenius acids is that when an Arrhenius acid reacts with an Arrhenius base, water is always a product. So we have here the hydrogen ion that is indicative of an Arrhenius acid, and hydroxide ion, which is indicative of an Arrhenius base. And so when you have that acid-base reaction, water is always a product. So we move in now to a different definition of acids and bases, and that is the Bronsted-Lowry acid and base. So a Bronsted-Lowry acid, by definition, is a proton donor, and a base is a proton acceptor. Well, we've used the term proton before, and we've described that as a subatomic particle. But what really is a proton? Well, let's think about a hydrogen atom for a minute. A hydrogen atom we know has one proton and one electron, and often has a neutron or two. And if a hydrogen atom loses an electron, right? So let's say that electron is gone. Well, now that becomes a hydrogen ion. Well, a hydrogen ion really is nothing but a proton, and maybe some neutrons too. But in terms of Bronsted-Lowry acids and bases, it is something that can accept a hydrogen ion or proton, or something that can donate a hydrogen ion or a proton. So as we look at different reactions, sometimes you can classify an Arrhenius acid also as a Bronsted-Lowry acid because it also donates a proton. So if we look at these two reactants, HCl, hydrochloric acid, and water, when they react, we form H3O+, that's a hydronium ion, and we form a chloride ion in that reaction. And so if we look at this from the perspective of what gained a proton, what lost a proton, well, water gained a proton, right? It went from H2O to H3O+, right? It gained a hydrogen ion. Well, if it is a proton acceptor, we would call that a base, a Bronsted-Lowry base. Well, where did it get that proton from? It got the proton from the proton donor, or the acid, right? The HCl became just regular old Cl. It lost the proton. What about a Bronsted-Lowry base? We can look at this the same way. Here's another reaction. We have ammonia and water this time. So what happens to the ammonia? The ammonia is gaining a proton. Well, if it's gaining a proton, that's going to mean that it is a proton acceptor. So that's a base. Well, where did it get the proton from? Well, H2O looks like it lost a hydrogen and became OH minus. And so that indicates that H2O is the acid in this example. Now, if you were paying close attention, you realize that water, in one example, was classified as an acid. And in another example, it was classified as a base. And there are some substances that can behave like an acid or can behave like a base. And that's perfectly okay. Those substances are called amphoteric substances. In this bottom example, and in the top example too, the right side of the equation, if we just look at those products, we give them a different name. So NH3 became NH4+. Well, it can now donate a proton. It's got an extra one that it could give away. And so we could classify NH4+ as an acid. But here we're going to call it a conjugate acid because it came from or was conjugated from the base. Also in this reaction, H2O on the left-hand side behaves like an acid. It donated a proton. On the right side, we call the product of that a conjugate base. Right? It is the base that came from or was conjugated from the Bronsted-Lowry acid on the left-hand side. And so OH, we recognize that as a base, right? Hydroxide ion is a base. And so because of that, we need to also label it as a base. All right, so NH3 is the proton acceptor, H2O is the proton donor, and we can make a similar designation, right? I will just label this conjugate acid and conjugate base on the right side. And really, this could also be a proton donor. And OH minus could be a proton acceptor. And so a lot of times in acid-base reactions, we use a double-headed arrow to indicate that this is what's called an equilibrium or a reversible reaction, meaning that it can kind of go both ways. So anytime we have a Bronsted-Lowry acid, there will always be a conjugate base. And anytime we have a Bronsted-Lowry base, there will always be a conjugate acid. They go together. When there's an acid, there's a base. When there's a base, there's an acid. So identifying them in a reaction is helpful, right? And sometimes it's as easy as looking at the equations on the left side and comparing them to the equations on the right side, right? H2SO4 became HSO4 with a 1 minus charge. Well, that lost a hydrogen ion. So that must be a proton donor. H2O became H3O plus. Well, that had to be a proton acceptor. And then the products get classified as a conjugate acid or a conjugate base. So let's do a quick sample problem here together just to make sure that you're understanding this as much as possible. You can pause the video here and predict your answers. In fact, I would recommend that you do that before you look at my solution. So I'm going to go ahead and label the proton donors and proton acceptors here. So HCO3 minus becomes H2CO3. Well, that looks to me as though that HCO3 with a 1 minus charge is a proton acceptor. And H2O is becoming OH minus, so that means it's the proton donor. And once we can identify that, then it's easy to identify this as our base and H2O as our acid. And so then H2CO3 is our conjugate acid. And OH minus is our conjugate base. All right, the conjugate base always comes from the original acid, and the conjugate acid always comes from the conjugate base. So we have the acid-base pair here, right, that I'll circle in blue. And then we have another acid-base pair that I will circle in green.